Hello everyone. So, today we will study the condensation, and particularly in today's lecture we will study the laminar film condensation on a vertical plate. We can ask this question, when does the condensation occur? So, when the vapor comes into contact with a liquid or a surface which has less temperature than the saturation temperature of that vapor, then condensation will occur. When the vapor comes into contact with a cold liquid, then condensation may occur and it may form fog. But in our lecture we will consider only condensation on a surface. So, if you consider that one vapor regime is there and it is at saturation temperature T sat. Now, if you bring one surface whose temperature is lower than the saturation temperature of the vapor, then condensation will take place. So, vapor will release the heat to the surface which is colder than the saturation temperature, and condensation will take place and liquid will be formed on the surface of the plate. So, if you consider one vapor, okay, this is your vapor at temperature T sat. Okay. Now, if you bring one plate to this vapor whose temperature is T w and T w is less than T sat. So, what will happen? This vapor will release the heat to this surface, okay, and liquid will be formed on this surface which is known as condensate, and this liquid will form a film on the surface depending on the nature of the surface. So, this liquid is known as condensate, okay, and due to gravity it will fall in the downward direction. Okay. So, you can see condensation occurs whenever a vapor comes into contact with a surface at a temperature lower than the saturation temperature of the vapor. The latent heat of the vapor is transferred to the surface and condensate is formed on the surface, releasing the enthalpy of the condensation. So, condensation involves a change in phase from vapor to liquid at a surface. So, one good example is that when you see a cold drinks bottle, you bring out from the refrigerator and keep in a ambient, then you will see that condensation takes place on the outer surface of the cold drinks bottle, and generally you have seen that droplets are formed and those droplets just come in downward direction. So, this is one example of condensation. So, there are many applications of condensation in industry as well as in our daily life. So, you can see here we have noted few applications: condensers for Rankine power generation cycles, vapor compression refrigeration cycles, dehumidifier for air conditioners, heat pipes. So, in heat pipes there are evaporators and condensers. So, in condensers condensation takes place. Condensation is also involved in many chemical power plants like oil refinery. So, as in our lecture we are considering only the surface condensation. So, there are two ways condensation can take place. One is film condensation and another is drop wise condensation, and it depends on the nature of the surface. So, you can see film condensation, generally one film is formed on the surface and this film just come in downward direction due to gravity. So, this is known as film condensation. So, entire surface is covered by the condensate which flows continuously from the surface and provides a resistance to heat transfer between the vapor and the surface. So, you can see when this condensation takes place on the surface, this liquid film is formed. Once the liquid film is formed, then this vapor is not in direct contact with the surface. So, this film acts as a thermal barrier. So, generally this vapor gives this heat to this liquid and this heat is transferred from this liquid to the surface. So, generally this film condensation takes place for a clean and uncontaminated surface, whereas in dropwise condensation you can see here. So, the small drops are formed after releasing the latent heat of condensation, then these smaller droplets coalesces and form bigger droplets, and these bigger droplets due to gravity just slides in downward direction. So, you can see here you have more bare surface where more heat transfer can take place, because the vapor is in direct contact with the surface and more heat transfer can take place. But in case of film condensation there is a resistance, because there is a film thickness. So, you can see the vapor condenses in the form of individual droplets. These droplets grow and coalesces with other nearby droplets to form larger droplets and eventually roll off the surface under the influence of gravity. So, surfaces coated with silicons and teflons, okay, if you have those surfaces, then these dropwise condensation can take place. So, as I told that in case of dropwise condensation, vapor is in direct contact with the surface and it can release the latent heat of condensation directly to the surface. But in case of film condensation there is a resistance in heat transfer. So, heat transfer is less compared to the dropwise condensation. So, if you see the heat transfer on the wall due to condensation versus this the Tsat minus Tw, then you can see that if it is, let us say 10 degree centigrade, okay, so this is your 20 degree centigrade, this is your 30 degree centigrade. So, this Tsat minus Tw in degree centigrade, and y axis is your heat flux, wall heat flux, and let us say this is your 100 kilowatt per meter square, okay. This is your 200 and this is your 300 kilowatt per meter square. So, in case of film condensation, so if you increase this Tsat minus Tw, then gradually it increases, whereas you have dropwise condensation, then it is much higher heat transfer takes place in case of dropwise condensation. So, you can see here how the heat flux on the wall varies with Tsat minus Tw. So, heat transfer rates with dropwise condensation can be more than 10 times higher than those with film condensation under the same conditions. So, now we will study the laminar film condensation on a vertical plate. So, we will consider a vertical plate and the vapor is in quiescent medium. So, when this vapor comes into contact with the surface which is at lower temperature than the T saturated, then condensation takes place, and we are considering only the film condensation. We will use some assumptions. So, these are the assumptions are made. The liquid film has laminar flow, it is steady laminar flow and constant properties at the mean film temperature. The vapor reservoir is at rest and is everywhere at the saturation temperature. The vapor exerts no shear stress at the liquid vapor interface. That means, if you have, this is the vertical plate, okay. So, y is measured perpendicular to this plate and x is measured along the vertical plate in the downward direction. Gravity acts in downward direction. The temperature of the plate is constant, that is your T W, and the vapor is at rest and its temperature is Tsat everywhere, and in this particular case Tw is less than Tsat. So, obviously condensation will take place and a liquid film will be formed over this surface. If you see the velocity distribution we will find in this class. So, here we are assuming that the vapor exerts no shear stress at the liquid vapor interface. So, this is your liquid vapor interface. So, at this y is equal to delta, where delta is the film thickness. Okay. So, if delta is the film thickness, then at y is equal to delta you have no vapor drag. That means at y is equal to delta you have del u by del y is 0. Okay. Then pressure change perpendicular to the wall across film is negligible. So, the film thickness is very small and you can neglect the pressure change perpendicular to this wall across film. One another important assumptions we will take in this particular case, that momentum and energy transfer by convection in the condensate film are negligible. So, we will see later that the film thickness is very small and the velocity of the film in downward direction is very small, and due to that we can neglect the inertia terms in the momentum equation as well as in energy equation, and obviously if we assume it, so it will simplify the analysis, and this analysis actually was first carried out by scientist Nusselt in 1916, and that is why this analysis is known as Nusselt analysis. And it is found that with these assumptions, if you find the heat transfer coefficient and Nusselt number or the total heat transfer rate, generally it predicts well with the experiments. With this our objective is to find what is the heat transfer coefficient and the Nusselt number. Both local heat transfer coefficient and average heat transfer coefficient we will calculate, and from there we will calculate the local Nusselt number and average Nusselt number. We need to calculate again the condensation rate or the mass flow rate for this particular case, and from there we need to calculate what is the film thickness delta, because delta varies in the x direction. So, we need to calculate the thickness, film thickness delta. Let us write the x momentum equation. So, u del u by del x plus v del u by del y into rho is equal to minus del p by del x plus mu L, we are writing L suffix because it is in the liquid in the condensate, okay, into del 2 u by del x square plus del 2 u by del y square plus rho L into G. Okay. So, in this particular case, as we have made these assumptions that your inertia force is very small. So, in the left hand side this you can neglect, okay, you can neglect, and also you can show that the variation del 2 u by del y square is much higher than del 2 u by del x square. Okay. Hence, you can also neglect this term in the diffusion term. So, if you simplify it, now you can write the governing equation as minus 0 minus del p by del x plus mu L into del 2 u by del y square plus rho L into G. Okay. And also you can see the liquid film on the surface is assumed to remain thin. So, pressure change across the liquid film are neglected. So, from you can say that del p by del y is 0. So, you can see So, now if you consider the vapor region, okay, so in the vapor region it is at rest. So, you can use the hydrostatic pressure. So, how do you calculate the hydrostatic pressure in the vapor region? So, in the vapor region if you calculate the hydrostatic pressure, so the vertical pressure gradient in the vapor, okay, so we will use this hydrostatic pressure equation. So, this is nothing but dP by dx is equal to rho v into g. Okay. So, v is for vapor. So, density of the vapor. So, L is L suffix L is for liquid and suffix v is for vapor. Okay. So, as this vapor is at rest, so you can see dP by dx is equal to rho v into g, because g is acting in the positive x direction. So, you can write dP by dx is equal to plus rho v into g. Okay. So, now this pressure gradient is imposed on the outer edge of the liquid film. So, if del p by del y is 0, then dP by dx this you can actually use in this equation. So, you can see that you can write 0 is equal to minus rho v g plus mu L del to u by del y square plus rho L g. So, this we could do because del p by del y is 0. So, you have imposed this pressure gradient inside the liquid film. Okay. So, now from here you can see that you can write the simplified equation as del to u by del y square is equal to minus g by mu L into rho L minus rho v. So, this is the equation. Now, you can integrate it and find the velocity distribution, but here you can see what are the boundary conditions. At the wall where y is equal to 0, obviously velocity is 0, and at the edge of the film which is your y is equal to delta, you have shear stress is 0. That means del u by del y is 0. That assumptions already we have made, that vapor is at rest and it exerts no shear stress on the film. So, boundary conditions at y is equal to 0, u is equal to 0, and at y is equal to delta you have del u by del y is equal to 0. Okay. So, if you integrate this equation, so you will get del u by del y is equal to minus g by mu L rho L minus rho v into y plus integration constant C1 and u, which is function of x and y, because as a function of delta, where delta is function of x, right. So, we will get g by mu L rho L minus rho v y square by 2 plus C 1 y plus C 2. Okay. So, now you apply the boundary conditions. So, if you put at y is equal to 0, u is equal to 0, you will get C 2 as 0. So, at y is equal to 0, u is equal to 0, that means C 2 is equal to 0, and at y is equal to delta del u by del y is equal to 0. Okay. So, if you see from here you can calculate C 1 as g by mu L rho L minus rho v into delta, and delta is function of x. Okay. So, if you put all these C 1 and C 2 value there, so you will get as liquid film velocity g into rho L minus rho v into delta square by mu L into y by delta minus half into y by delta square. So, in this equation you can see in the right hand side rho L minus rho B is positive, because rho L is much higher than the rho B, and y by delta is also positive. Okay. So, because delta is greater than y, okay, and rho L is greater than rho B. So, you can see the right hand side term will be positive. So, u is always positive. Okay. So, u is always positive. Now, you want to calculate the mass flow rate. So, if you want to calculate the mass flow rate, you can integrate this velocity, okay, so over the film thickness delta. Okay. So, the mass flow rate of the liquid at a distance x from the top edge so you considered the vertical plate and this is your liquid film over this surface. Now, if you take a distance y from the surface and a elemental distance dy. Okay. So, in the perpendicular direction of the surface, if you take unit width, then your this elemental area will be dy into 1, and this is your y and this is your x. Okay. So, what will be your area? dA will be dy into 1. Okay. 1 is your unit width. Okay. So, now if you want to calculate the mass flow rate, so m dot, you know that you integrate from 0 to delta. So, this is your film thickness delta. So, 0 to delta rho L u dA. Okay. So, you can see this will be rho L is constant, 0 to delta, okay, and u dA is dy. So, you can see if you put the expression of u and the constant if you take outside the integral, then you can write this as this, and 0 to delta y by delta minus half y by delta square dy. Okay. So, now you perform the integration and put the limits, then you can find the mass flow rate as g rho L minus rho v delta square divided by mu L. Delta square we have taken outside because delta is function of x only and you are integrating with respect to dy. Okay. So, you can see you can write as y square by 2 delta minus 1 by 2 into y cube by 3, right. So, y cube by delta square 0 to delta, and finally, you will get g rho L minus rho v delta cube divided by 3 mu L. So, you can see the in the expression of velocity as well as mass flow rate, delta is there, okay, and this delta is function of x and it is still unknown. So, we need to find this film thickness delta. So, next we will find the temperature distribution. So, if you see in the energy equation we can neglect the inertia term. So, left hand side terms will be 0, and in this particular case also we can neglect the axial heat conduction because it is very small compared to the del 2 T by del y square. Hence, you will get the energy simplified energy equation as. So, if you write energy equation rho Cp u del T by del x plus V del T by del y is equal to k del 2 T by del x square plus del 2 T by del y square. So, all these terms in the left hand side these are negligible, okay, because inertia terms, and del 2 T by del x square is much smaller than del 2 T by del y square. Okay. So, this term also you can neglect. So, simplified energy equation you can write del 2 T by del y square is equal to 0. So, that means only heat conduction is taking place. Okay. So, what are the boundary conditions? At y is equal to 0 you have wall temperature Tw, and at y is equal to delta you have T is equal to saturation temperature Tsat. So, if you integrate this equation, what you will get? You will get del T by del y is equal to C1 or you can write C3. So, after integrating this equation you will get del T by del y is equal to C1, and another time if you integrate, then you will get T as C1y plus C2. Okay. So, if you put the boundary condition at y is equal to 0, T is equal to Tw, then you can see that you will get C2 is equal to Tw, and at y is equal to delta T is equal to Tsat. Okay. So, you can see you will get Tsat is equal to C1 into delta plus Tw. That means, C1 is Tsat minus Tw divided by delta. So, if you put C2 and C1 value here, you will get T as 1 by delta Tsat minus Tw y plus Tw. Okay. And you can write temperature profile. So, you can see here only we considered the heat conduction inside the film. Okay. So, we will get Tsat minus T divided by Tsat minus Tw as 1 minus y by delta. So, if only heat conduction is taking place, so what do you expect the temperature profile? It will be linear, and you can see here that it is a linear profile. Okay. So, it is a linear profile. So, it will vary linearly from Tw to Tsat, because Tsat is higher than the Tw. Now, delta is unknown. To calculate the delta, now we will use conservation of mass and conservation of energy inside a elemental volume in liquid film. So, if you consider the vertical plate and this is your film thickness, this is your y, this is your x, g is acting in downward direction, and if you consider this elemental volume, okay, where you can see if it is vapor. So, from the vapor it will release the latent heat through this interface, okay, and this will conduct to the surface, and in the surface it will release the heat. Okay. And obviously, there will be mass flow rate is coming here, and it will mass flow rate will go out, and with that your energy also will come in and energy will go out. So, this is the elemental control volume we are considering, and this control volume if you see, so this we are considering at a distance Ax of distance dx. Here it is dx, okay, and this is your control volume. So, we are using conservation of mass now. So, you can see from the vapor, okay, so d m dot v will go, because this will convert from vapor to the liquid, releasing the latent heat. your m dot is coming, mass flow rate is coming, and as dm dot v is added. So, you will get m dot, and if you use the Taylor series expansion, then whatever m dot is coming. So, that you can write at the exit of this control volume as m dot plus dm dot by dx into dx. So, this is we are using Taylor series expansion only, okay. And this is wall, okay. So, there is no mass is going through this surface because this is wall. So, if you consider this and if you do the mass balance, so you will get rate of mass is condensed on the outer surface of CV is equal to rate mass leaves the control volume minus rate mass enters in control volume. Okay. So, what is that? In left hand side it is dm dot v, right hand side what is leaving? So, m dot plus dm dot by dx into dx, and whatever enters, that is your m dot. So, you can see your whatever vapor is converting to the liquid dm dot v is nothing but equal to dm dot by dx into dx. So, now we will use the conservation of energy. In this particular case, as liquid film acts as the thermal resistance, the vapor converts to the liquid, releasing the latent heat to the film, okay. And then this heat is conducted through the liquid to the surface. So, if you consider the latent heat whatever it is giving to the liquid at the interface, after that there will be a temperature difference, okay, that we are assuming. So, that is known as subcooling. So, if you consider the effect of subcooling and write the conservation of energy equation, then we can write it as, so whatever control volume we considered. So, this is the control volume we considered, this is your dx, okay, and at a distance y, let us take a strip of distance dy, okay. So, now we will use the conservation of energy in this control volume. Okay. So, you can see the whatever vapor is converted to the liquid at the liquid film interface. So, that is your dm dot v into HFG, okay. And there will be a sensible heat because whatever dm dot v HFG, okay, this is going, and here on the surface your q double prime w is released, okay, and you have m dot is coming in, okay, and this m dot in this particular small elemental volume, it is rho L u into dy, okay, into your enthalpy H L, because we are considering the sensible heat. So, if you are considering a sensible heat, then rho L u dy H L is coming here, and obviously again if you integrate this from 0 to delta, because delta is your thickness. So, if you 0 to delta if you integrate, then you will get the total energy coming in, okay, and that if you use the Taylor series expansion, then you can write at the outlet, okay. So, when subcooling of the liquid film is allowed, then total enthalpy flowing into and out of the CB must be included in the energy balance. So, if you do not consider the sensible heat, then you can see it is simply whatever heat is released, that means dm dot V HFG is equal to Q double prime W. Okay. But if you consider the effect of subcooling and if you consider this sensible heat, then this you need to consider whatever energy is coming in. Okay. So, this and whatever is coming out, so that sensible heat you need to consider. So, conservation of energy, now if you write, so it will be heat transfer rate to wall is equal to rate of mass influx at the outer edge of the film into latent heat per unit mass. Okay. Now, minus you have to write rate enthalpy leaves the CB minus rate enthalpy enters the CP. Okay. So, now left hand side, so heat transfer rate to the wall, what is that? So, your heat flux is Q double prime W, okay, into dA. What is the area? So, this is dx and per unit width if you write, then dx into 1. So, this area dA you can write as dx into 1. So, dx into 1 and rate of mass influx at the outer edge of the film. So, that is dm dot V, okay, into HFG, and now whatever is coming in and leaving. Okay. So, that you can write 0 to delta rho L U H L dy. Okay. So, this is coming in, but when you consider what is leaving the control volume, then you use the Taylor series expansion and this will be this plus change of this d of dx 0 to delta rho L U H L dy into dx. Okay. So, this is the rate enthalpy leaves the CB and minus whatever is coming in. So, that is your 0 to delta rho L U H L into dy. Okay. So, this we are considering if you are taking into account the sensible heat. Okay. So, this is known as effect of subcooling. So, if you are considering that, then only you need to add it. So, if you see that if you do not consider the sensible heat, then it is just Q double prime W dx is equal to dm dot V HFG. This is the simple thing. But as we are considering the sensible heat, you need to add this term and you have to integrate, because u is a function of y. Okay. So, x and y. So, that you need to integrate. So, what is Q double prime W? So, this is nothing but K L del T by del y at y is equal to 0. You see, we are writing plus because Q double prime W is in the negative y direction, because this is your y direction. Okay. So, obviously, this is negative into y direction. So, generally we write Q double prime W minus K del T by del y, but here Q double prime W is negative to y. So, this is plus K L del T by del y at y is equal to 0. So, this if you write here, so you will get K L del T by del y at y is equal to 0, dx is equal to dm dot V HFG minus d of dx 0 to delta rho L U H L dy dx. Now, here the enthalpy you see, the enthalpy of this subcooled liquid is measured relative to that existing at the saturation temperature, i.e., assuming that the liquid specific heat is constant and the enthalpy of the subcooled liquid film HL can be expressed as HL is equal to CPL into T minus T sat. So, this expression you can write. So, as we are calculating the enthalpy okay, with respect to the enthalpy at the interface okay, at T sat. So, that is why we are writing HL into CPL T minus T sat. So, obviously your now dm dot v, you know this is dm dot by dx into dx, right. So, and KL del T by del y. So, this you can see your temperature distribution is T sat minus T x y is T sat minus T w into 1 minus y by delta. So, from here if you calculate K L del T by del y at y is equal to 0, you will get K L T sat minus T w divided by delta. So, in this term you put this value, then dm dot v you put this value and write the energy equation as K L T sat minus T w divided by delta dx is equal to H f g dm dot by dx into dx minus d of dx 0 to delta rho L u. Now, H L we are putting as CPL into T minus T sat okay, into dy okay, and you have into dx. Okay. So, just putting all the terms here okay, we wrote this expression. Now, you can see in every term dx is there. So, this dx term you can cancel. So, you can write it as K L T sat minus T w divided by delta is equal to H f g dm dot by dx minus d of dx 0 to delta rho L u CPL T minus T sat into dy. Okay. So, now let us calculate dm dot by dx. You know the mass flow rate m dot. So, what is that? M dot is G rho L minus rho v delta q by 3 mu L. This we have already calculated. Okay. So, dm dot by dx you can write as G rho L minus rho v divided by 3 mu L. These are constant and you can write as d delta cube by dx. Okay. And we know u as G rho L minus rho v delta square by mu L y by delta minus half into y by delta square. Okay. And here temperature is there. So, you know T sat minus T is equal to 1 minus y by delta into T sat minus T w. Okay. So, if you put, let us evaluate this term first. So, if you put u and T minus T sat, then you integrate it. Okay. So, if you write this term, the integration 0 to delta rho L u CPL T minus T sat into dy. Let us integrate this term first. So, what are constant, you take it outside. So, these are CPL rho L, you can take it outside, you can write d of dx okay, then 0 to delta. Now, you put the expression of g u. So, g into rho L minus rho v delta square by mu L y by delta minus half y by delta square. Okay. Now, you see here expression is T minus T sat. So, if you write it, so there will be one minus sign. So, it will be minus 1 minus y by delta T sat minus T w, okay, into dy. So, now you integrate this one. Okay. So, if you see this, you can write as equal to minus CPL rho L G rho L minus rho V T sat minus T w, okay, divided by mu L d of dx. Okay. Delta is function of x and you are integrating with respect to y. So, you can take it outside delta cube. So, if you take delta cube outside, so we write delta cube, then we will 0 to delta. Now, you multiply this with this. So, what you can write? It is y by delta minus 3 by 2 y by delta square plus half y by delta cube, okay, into d of y by delta. So, you can see here delta square is there, we have divided by delta. So, it will be delta cube. So, now easily you can integrate it. Okay. You will get CPL rho L G rho L minus rho V T sat minus T w divided by mu L, okay, d of dx delta cube. So, this you integrate. So, you can see this will be 0 to 1, okay, because y by delta. So, y by delta will vary 0 to 1. So, if you see this will be just y square by 2. So, it will be half, then 3 by 2 y cube, okay. So, y cube by 3. So, this will be just 1 by 3 plus half. So, it will be 1 by 4, okay. So, this 3 will get cancelled. So, you can write half will cancel. So, it will be 1 by 8, okay. So, it will be 1 by 8. So, you will get here just 1 by 8, okay. So, next if you put it here, then you can see, and dm dot by dx you put it here. So, finally, you will get K L T sat minus T w divided by delta is equal to G rho L minus rho V divided by 3 mu L. Then you will get H f g plus 3 by 8 C P L T sat minus T w d delta cube by dx. So, you see here d delta cube by dx is there, here d delta cube by dx is there. So, that we have taken common, and here minus is there and here minus is there. So, it will become plus. So, with that you can write as H f g plus 3 by 8 C P L T sat minus T w. So, you can see when we consider the sensible heat, one additional term is coming as 3 by 8 C P L T sat minus T w with the HFG. So, we can say that it is a modified latent heat of condensation, okay, H prime Fg, which is your HFG plus the term which is coming considering the subcooling effect. Okay. You can say that to include subcooling effects, modified latent heat H prime can be defined as H prime f g is H f g plus 3 by 8 C P L T sat minus T w. So, if you do not consider the sensible heat part, then the last term will be 0. So, simply H f g you can use, and that will come from the energy balance, where you can write that dm dot b H f g is equal to just Q double prime W into dA. So, that is the energy balance, but when we considered the subcooling effect, so this additional term is coming. Now, if you consider that your vapor is at higher temperature than Tsat, that means superheated vapor, then you have to bring this temperature to Tsat, then only the condensation will take place. So, that time if you consider the modified latent heat, then you need to consider that effect also to cool down the vapor from the superheated temperature to the saturation temperature. So, in that particular case you can write for superheated vapor in condenser at Tv, okay, vapor must be cooled first to Tsat before it condenses. Okay. So, in that case H prime Fg will be just Hfg plus the subcooling effect 3 by 8 Cpl into Tsat minus Tw, and you need to consider the Cpv into Tv minus Tsat. Okay. So, now here we will define one new non-dimensional number. So, when you considering the subcooling effect H prime Fg, here if you take common Hfg, then you can write 1 plus 3 by 8 Cpl Tsat minus Tw divided by Hfg. Okay. So, this Cpl Tsat minus Tw divided by Hfg will write as Jacob number, one new non-dimensional number which is known as Jacob number. So, now you can see that we can define Jacob number as Cpl Tsat minus Tw divided by Hfg, where it is the ratio of sensible energy absorbed by liquid to the latent energy absorbed by the liquid. Okay. And already, so if you define this Jacob number like this, then the modified latent heat H prime Fg, you can write Hfg 1 plus 0.68 into Jacob number. Okay. And if the effects of the subcooling on the energy balance is neglected to simplify the analysis, then whatever now we will derive, just in place of H prime Fg you put Hfg, then the subcooling effect will be neglected. Okay. So, now we have done the integration. So, let us put in the original equation and find what is the film thickness delta. So, we can write now KL Tsat minus Tw divided by delta is equal to, so in the right hand side all those two terms if you put and take common, then you will get G rho L minus rho V H prime Fg divided by 3 mu L into d delta cube by dx. Okay. So, now let us take d delta cube dx in the left hand side and rest other term let us take in the right hand side. So, you can see if you take d delta cube of dx, then you can write it as, and one delta is coming from here. So, delta into 3 delta square d delta by dx, okay, and KL Tsat minus Tw, okay, into this 3 mu L divided by G rho L minus rho V into H prime Fg. So, that if you write, then you will get 3 into mu L KL Tsat minus Tw divided by H prime Fg G rho L into rho L minus rho B. So, you can see these 3 will get cancelled. So, in the left hand side you have delta cube d delta by dx is equal to mu L k L T sat minus T w divided by h prime f g g rho L minus rho B. So, we can integrate this now. So, you can write delta cube d delta is equal to mu L k L T sat minus T w divided by h prime f g g rho L minus rho B into dx. Okay. So, you can see if you integrate from x equal to 0 to L, L is the length of the plate. Then at x equal to 0, what is the thickness of the film? It is 0, okay, and at x equal to L, it is delta. Okay. So, let us integrate left hand side 0 to delta and this is 0 to x. Okay. X at any length x you can put. So, you can write delta to the power 4 by 4 is equal to mu L k L T sat minus T w, these are all constants. So, you can take it outside h prime f g g rho L minus rho B. So, it will be just x. So, if you integrate 0 to L, then you will get here L which represent the film thickness at x equal to L. Okay. So, in general we have written the film thickness. Okay. So, you can see delta which is function of x, you can write as 4 mu L k L T sat minus T w divided by h prime f g rho L minus rho V, okay, into x to the power 1 by 4. So, you see this film thickness varies with x. So, what is the order? X to the power 1 by 4. So, delta varies x to the power 1 by 4. Okay. And when we will solve some example problems, you will see that at the end of vertical plate this delta will be order of less than 1 millimeter. So, it is very thin. So, now we have found the film thickness delta. So, you will be able to calculate the velocity as well as temperature profile, then the mass flow rate, because all these we have represented in terms of delta. So, you can see the delta x we have found now. So, the liquid film velocity is this one. So, delta if you put, you will be getting the film velocity, and now m dot which is your mass flow rate per unit width. Okay. So, this is the expression where delta you can put this value, and liquid film temperature is this one. Okay. So, now we are interested to find what is the local and average heat transfer coefficient, and then local and average Nusselt number. So, you can see liquid film thickness we have found like this. So, now heat transfer coefficient, which is your local heat transfer coefficient, you can define as q double prime w divided by T sat minus T w. So, you can see if this is your plate, okay. So, q w double prime is this one, and this is your y direction. So, obviously, you can see the heat transfer coefficient you can write as the temperature of the plate is T w, this is your film thickness, and vapor temperature is T sat. So, obviously, the heat transfer coefficient you can write as heat flux divided by T sat minus T w, and this heat flux you can write as K L del T by del y at y is equal to 0. Okay. And this is a positive sign, because y direction the q w whatever we have considered in negative y direction. So, obviously, it is K L del T by del y at y is equal to 0, and this already we have found as K L T sat minus T w into divided by delta. So, here you can see this temperature profile you know. So, you just find del T by del y at y is equal to 0. So, you can see heat transfer coefficient is K L by delta. So, delta if you put in this expression, then you will get the local heat transfer coefficient as this. So, you have to remember this expression, and average heat transfer coefficient, now you have to just integrate it over the plate length L. Okay. So, if plate length L, x is measured from here in the downward direction. So, 1 by L 0 to L h dx. So, if you integrate h, so here x is there, so x to the power minus 1 by 4, right. So, x to the power minus 1 by 4 dx 0 to L. So, integration 0 to L x to the power minus 1 by 4 dx. So, if you put it, then you will get the average heat transfer coefficient like this. So, this 4 by 3 and inside you have 1 by 4 to the power 1 by 4. So, if you evaluate it, you will get around 0.943. Okay. So, this is the average heat transfer coefficient. Now, you see this is your local heat transfer coefficient. If you put the local heat transfer coefficient at x equal to L. So, you will get just x equal to L. If you put, you are going to get similar expression, only the outside there will be 4 by 3, okay, because you see this is the expression is same as this inside the bracket except x equal to L. So, the average heat transfer coefficient we can write is equal to 4 by 3 local heat transfer coefficient at x equal to L. Now, we can easily calculate the Nusselt number, because as you have found the local and average heat transfer coefficient, using that you will be able to calculate the Nusselt number. So, you can see Nusselt number is Hx by KL. So, H already we have found. So, this H if you put here and rearrange, you will get this expression. Okay. So, now if you put this H bar, whatever we have put already evaluated. So, average Nusselt number you will get H bar L by KL. So, this if you put here and rearrange, you will get 0.943 into this expression. And remember, here we have defined the Nusselt number based on the length of the plate. Okay. So, L cube, and similarly the average Nusselt number you can write is equal to 4 by 3 Nusselt number at x equal to L. So, this is your local Nusselt number. Okay. This is your local Nusselt number and this is your average Nusselt number. So, today we considered laminar film condensation on a vertical plate, and we neglected the inertia term in the left hand side. So, because the film thickness is very small and it travels in very slow motion, hence we neglected the convection term in the momentum equation and energy equation, and from there we calculated the velocity distribution as well as temperature distribution. Then we calculated the mass flow rate per unit width. Then from there we have calculated equating the using the conservation of mass and conservation of energy, we have found the film thickness. Once you know the film thickness, you know the velocity distribution, temperature profile as well as mass flow rate. Then we have calculated the local and average heat transfer coefficient. As you know the film thickness delta, so you will be able to calculate easily. Once you calculate the average heat transfer coefficient and local heat transfer coefficient, you will be able to calculate the average Nusselt number and local Nusselt number, and that we have found. Now, from there you can conclude that average Nusselt number will be 4 by 3 into local Nusselt number at x equal to